Hi, this is a collective work by Reet and Chuanling, and we are presenting the paper Learning Emotion Representation from Verbal and Nonverbal Communication. So, about the paper, it is essentially a paper that introduces EmotionClip, which is a novel pre-training paradigm for extracting visual emotion representation from verbal and nonverbal communication. It addresses the challenges related to data scarcity in emotional understanding dataset world. It also uses expressed emotions instead of just relying on perceived emotions, and it adds the new modality of visual data to the audio data for actually creating this sentiment analysis. So, what dataset are we working with? Well, we essentially have a dataset of approximately 1 million raw video clips from 3,613 TV series on YouTube. This was chosen because TV shows naturally contain rich expression in both verbal and non-verbal communication, and it happens in various scenes. The pre-processing included grouping the words in the closed caption to make complete sentences, tagging each of these sentences with the sentiment score, and finally extracting human bounding boxes from the video frames. Now, about the model architecture. Well, um, first we have the visual branch, which has the subject-aware frame encoder. This essentially uses a VIT as a backbone. It takes in the RGB frames and binary masks as an input. It extracts non-overlapping image patches and projects them into a 1D token. And also, it adds two learnable tokens, which are the CLS or the classification token, which is similar to the CLS in BERT, and also the HMN, which is the human token to encode information about human subject in frame. Um, the output is passed to the temporal encoder, which aggregates frame level representation into a video level representation. For the audio branch, we have a text encoder that is essentially a default transformer architecture, and we have a pre-trained sentiment analysis model, which has frozen weights so that it doesn't learn during training. And finally, for the actual training, we use contrastive learning, um, wherein essentially and there's a modification wherein it actually uses sentiment guided contrastive learning to address the false negative problem. In contrastive learning, um, and the main difference is that it defines a similarity threshold based on previous scores, and any pair above that similarity threshold is considered a potential false negative and excluded from the negative pairs.
Okay, and the author also spent a great effort to enhance the subject-aware context decoding techniques. The first method the author considered is called the subject-aware attention masking, SAM. Normally, the whole image and the crop subject are treated as two separate images, which doesn't directly connect the context and the subject. With SAM, the attention mechanism in the vision transformer is changed so it focuses more on the subject. Instead of using cropped images, the whole image is fed into the model, but it pays actual attention to the subject's location. In regular attention module, attention is controlled by query key and value functions. However, the author improved this by adding a learned assignment matrix A and the weighting matrix U that help shift attention to the subject, allowing for more focused processing. The second method the author explored is called the subject-aware prompting, SAP. Unlike SAM, which changes how attention works in the model, SAP keeps the attention module the same, but changes the input. Previous research showed that drawing a colored box around the subject helps guide attention. Instead, this paper suggests giving such hints in the latent space using positional embeddings. As shown in the example, the attention from the prompt token gradually shifts toward the subject as the model layer progresses from left to right. After exploring the methods outlined in the paper, we can now discuss the results. The paper compares model accuracy across different components. First graph shows that both SAP and SINS consistently outperforms the baseline by a small margin. Additionally, in the second graph, the sentiment guidance intensity, which represented by the parameter beta, can improve the model performance, but it requires careful fine-tuning, as higher values do not necessarily lead to better outcomes. The model's overall performance is similar to and often better than the latest state-of-the-art models back in 2023 in 5 datasets, except for some models that uses audio. EmotionClip outperforms most models that only use vision and text. In conclusion, this paper shows that pre-training approach has great potential for improving emotion understanding by using large, uncurated datasets for training. This approach is especially helpful in tackling the challenges of scaling and data shortage in the current stage of AEI research. And that wraps up the 6-minute presentation. Thank you for watching.